Picture this: the universe, vast and mysterious, holds a secret that has baffled scientists for decades. A significant portion of its matter, specifically the kind that makes up stars, planets, and even you, has gone missing. This isn't science fiction. It's one of the greatest unsolved mysteries in cosmology, the missing baryon problem. Baryons, the building blocks of ordinary matter, are everywhere, and yet, somehow, we can't account for nearly half of them. Where are they hiding? What cosmic trickery is at play? For years, this puzzle has pushed astronomers to the edge of their understanding, probing the depths of space with cutting-edge technology and groundbreaking theories. Today, we're diving into this cosmic detective story, uncovering 25 clues that could finally solve the mystery of the missing baryons. From the invisible threads of the cosmic web to the faint whispers of intergalactic gas, each clue brings us closer to understanding the universe's hidden blueprint. So buckle up, because by the end of this journey, you'll see the cosmos in a whole new light. Let's begin. Now, let's turn our attention to the first clue in this cosmic mystery, the cosmic web. Imagine the universe not as a random scattering of galaxies, but as an intricate tapestry woven together by invisible threads. This is the cosmic web, a vast network of filaments made of dark matter and gas, stretching across the cosmos like the veins of the universe. These filaments connect galaxies and galaxy clusters, forming the backbone of the large-scale structure of the universe. But here's the fascinating part. Scientists believe that within these filaments, the missing baryons might be hiding. How does this work? Well, simulations of the universe's evolution show that as the universe expanded after the Big Bang, dark matter began to clump together, forming this web-like structure. Ordinary matter, or baryons, followed the gravitational pull of dark matter, flowing into these filaments. However, the gas in these filaments is incredibly diffuse and faint, making it extremely difficult to detect with traditional telescopes. It's like trying to spot a single strand of spider silk in a vast, dark room. But recent observations and advanced simulations are giving us hope. By studying the light from distant quasars and galaxies, astronomers have detected faint traces of ionized gas in these filaments. This gas, though sparse, could account for a significant portion of the missing baryons. Think of it as finding tiny droplets of water in a desert. Each one might seem insignificant, but together they add up to something much larger. The cosmic web isn't just a theoretical concept anymore. It's a real, observable structure that could hold the key to solving the missing baryon problem. And as our technology improves, we're getting closer to mapping this web in greater detail, bringing us one step closer to uncovering the universe's hidden secrets. So, while the cosmic web might seem like an abstract idea, it's a crucial piece of the puzzle, one that could finally help us locate the missing baryons and understand the full story of the universe's matter. Now, let's shift our gaze to the second clue in our cosmic detective story, the warm-hot intergalactic medium, or WHIM. Picture the space between galaxies not as an empty void, but as a vast, invisible ocean of gas. This is the WHIM, a diffuse, superheated gas that fills the intergalactic space, threading through the cosmic web we just explored. While it might sound like something out of science fiction, this gas is very real, and it could be hiding a significant chunk of the universe's missing baryons. So, what exactly is the WHIM? It's a thin, ionized gas that exists at temperatures ranging from hundreds of thousands to millions of degrees. Unlike the dense gas found within galaxies, the WHIM is incredibly spread out, making it almost invisible to most telescopes. Detecting it is like trying to see steam rising from a cup of tea in a foggy room. It's there, but it blends into the background. Yet, despite its elusive nature, scientists believe the WHIM could contain up to half of the universe's baryons. That's a staggering amount of matter that's been hiding in plain sight. But how do we even begin to find something so faint? The key lies in the way the WHIM interacts with light. When light from distant quasars or galaxies passes through this gas, it gets absorbed at specific wavelengths, leaving behind faint fingerprints in the form of absorption lines. These lines act like cosmic breadcrumbs, guiding astronomers to the presence of the WHIM. Instruments like the Hubble Space Telescope and X-ray observatories have been crucial in detecting these subtle signals, giving us glimpses of this hidden reservoir of matter. One of the most fascinating aspects of the WHIM is its role in the cosmic ecosystem. As galaxies form and evolve, they eject gas into the intergalactic medium through processes like supernova explosions and galactic winds. This gas, heated to extreme temperatures, becomes part of the WHIM. Over time, it can cool and flow back into galaxies, fueling the birth of new stars and planets. In this way, the WHIM isn't just a passive bystander, it's an active participant in the life cycle of the universe. While the WHIM remains challenging to study, advancements in technology are bringing us closer to unraveling its mysteries. Future telescopes like the upcoming James Webb Space Telescope and the Athena X-ray Observatory promise to provide even sharper views of this elusive gas. As we continue to piece together the clues, the WHIM stands as a vital piece of the puzzle, helping us understand where the missing Baryons have been hiding all along. So, while it might be hard to see, the WHIM is a crucial part of the cosmic story, one that's slowly coming into focus. Now, let's turn our attention to the third clue in our cosmic investigation: X-ray observations. While the WHIM is notoriously difficult to detect, X-ray telescopes like Chandra have become indispensable tools in the search for this elusive gas. These powerful instruments allow us to peer into the high-energy universe, where the WHIM superheated gas emits faint X-ray signals. Think of it as using night vision goggles to spot something hidden in the dark. Chandra gives us the ability to see what would otherwise remain invisible. One of the key breakthroughs came when Chandra detected faint X-ray emissions from the WHIM in the form of absorption lines. These lines are like cosmic signatures, revealing the presence of ionized oxygen and other elements within the gas. By analyzing these signals, scientists have been able to map out the distribution of the WHIM, confirming that it's not just a theoretical concept but a real, tangible part of the universe. For instance, observations of distant quasars have shown that their light passes through patches of the WHIM, leaving behind telltale X-ray fingerprints. These findings have provided some of the most direct evidence yet that the WHIM contains a significant portion of the missing Baryons, but Chandra's contributions don't stop there. By studying galaxy clusters which are surrounded by vast halos of hot gas, the telescope has also shed light on how the WHIM interacts with these massive structures. The gas in these clusters is so hot that it emits X-rays, and Chandra has revealed that some of this gas likely originates from the WHIM itself. This suggests a dynamic relationship between the WHIM and galaxy clusters, where gas flows in and out, shaping the evolution of these cosmic giants. What makes X-ray observations so powerful is their ability to probe the high-energy universe, where the WHIM extreme temperatures make it detectable. Without telescopes like Chandra, much of this gas would remain hidden, leaving a gap in our understanding of the universe's Baryon budget. As we continue to refine our techniques and develop even more advanced X-ray observatories like the upcoming Athena mission, we're inching closer to solving the mystery of the missing Baryons. Each observation brings us one step closer to completing the cosmic puzzle, revealing the hidden threads that connect the universe's largest structures. Now, shifting our focus to the next piece of the puzzle, we arrive at the fourth clue: ultraviolet spectroscopy. While X-ray observations have given us a glimpse into the high-energy universe, ultraviolet spectroscopy offers a complementary perspective, allowing us to detect ionized gas in the intergalactic medium. This technique is like using a special filter to see the faint glow of gas that's been energized by the light of distant stars and galaxies. ultraviolet spectroscopy works by analyzing the light from distant objects such as quasars as it passes through the intergalactic medium. When this light encounters ionized gas, certain wavelengths are absorbed, creating distinct absorption lines in the spectrum. These lines act like fingerprints, revealing the presence of elements such as hydrogen, helium, and carbon in the gas. By studying these absorption features, scientists can map out the distribution and properties of ionized gas across vast cosmic distances. One of the most powerful tools for this kind of observation is the Hubble Space Telescope. Hubble's ability to capture ultraviolet light has made it an invaluable instrument in the search for missing baryons. For example, Hubble has observed the light from distant quasars passing through the intergalactic medium, revealing a complex network of ionized gas filaments. These filaments, often referred to as the Lyman-alpha forest, provide critical clues about the structure and composition of the universe's hidden baryons. What makes ultraviolet spectroscopy so effective is its sensitivity to ionized gas, which is a key component of the WHIM. While X-ray observations detect the hottest regions of the WHIM, ultraviolet spectroscopy captures the cooler, ionized gas that fills the spaces between galaxies. Together, these techniques give us a more complete picture of where the missing baryons might be hiding. Hubble's contributions have been groundbreaking, but they're just the beginning. Future missions like the James Webb Space Telescope will build on this work by extending our ability to observe even fainter and more distant sources of ultraviolet light. As we continue to refine our methods and expand our observational capabilities, ultraviolet spectroscopy will remain a vital tool in unraveling the mystery of the missing baryons. Each new discovery brings us closer to understanding the intricate web of gas that connects the universe's largest structures, helping us piece together the cosmic puzzle one clue at a time. Now, let's turn our attention to another fascinating clue in the search for missing baryons, the Sunyaev-Zeldovich effect. This phenomenon, named after the scientists who first described it, provides a unique way to detect hot gas in galaxy clusters, offering yet another piece of the cosmic puzzle. Unlike ultraviolet spectroscopy, which focuses on ionized gas, the Sunyaev-Zeldovich effect allows us to study the extremely hot gas that fills the vast spaces between galaxies in clusters. Here's how it works. When light from the cosmic microwave background, the afterglow of the Big Bang, passes through a galaxy cluster, it interacts with the hot gas trapped there. This gas is so energetic that it scatters the microwave photons, shifting their energy slightly. This shift creates a distinct distortion in the cosmic microwave background, which astronomers can detect and analyze. It's like seeing a shadow cast by the hot gas, revealing its presence even when it's otherwise invisible. The beauty of the Sunyaev-Zeldovich effect lies in its ability to uncover hot gas that doesn't emit much light on its own. This gas, often referred to as the intracluster medium, is a significant reservoir of baryons. By mapping these distortions across the sky, astronomers can identify galaxy clusters and measure the amount of hot gas they contain. This information is crucial because it helps us account for a portion of the missing baryons that might be hiding in these massive structures. One of the most exciting aspects of this effect is its independence from distance. Unlike other methods that rely on the brightness of objects, the Sunyaev-Zeldovich effect works equally well for nearby and distant galaxy clusters. This makes it a powerful tool for studying the evolution of the universe over cosmic time. By observing how the distribution of hot gas changes across different epochs, scientists can gain insights into how galaxy clusters formed and grew, and how baryons were distributed throughout the universe's history. Recent observations using telescopes like the Atacama Cosmology telescope and the Planck satellite have provided stunning maps of the Sunyaev-Zeldovich effect across the sky. These maps not only confirm the presence of hot gas in galaxy clusters, but also help refine our understanding of the universe's large-scale structure. As we continue to improve our observational techniques, the Sunyaev-Zeldovich effect will remain a key tool in the quest to locate the missing baryons, bringing us one step closer to solving this cosmic mystery. Now, let's shift our focus to a clue that sounds like something straight out of a science fiction novel: fast radio bursts, or FRB. These mysterious, incredibly brief bursts of radio waves have puzzled astronomers since their discovery. But beyond their enigmatic nature, FRBs are proving to be powerful tools in the search for missing baryons. Here's why. Fast radio bursts are intense flashes of radio light that last just milliseconds, yet they pack an enormous amount of energy. What makes them so valuable is their journey across the universe. As these bursts travel through space, they pass through various regions filled with gas, plasma, and other materials. Each of these regions leaves a kind of fingerprint on the radio waves, subtly altering their properties. By studying these changes, astronomers can measure the density of baryons along the path of the FRB. Think of it like this: imagine shining a flashlight through a foggy window. The fog scatters the light, and by analyzing how the light changes, you can learn something about the fog itself. FRBs work in a similar way, but on a cosmic scale. As they travel through the intergalactic medium, the baryons they encounter cause tiny delays in the radio waves depending on their frequency. This effect, known as dispersion, allows scientists to calculate the total number of baryons the FRB has passed through. One of the most exciting aspects of using FRBs is their ability to probe regions of the universe that are otherwise difficult to study. Unlike other methods that rely on light emitted by stars or gas, FRBs can travel through vast distances, passing through areas where baryons might be hiding in diffuse, hard-to-detect forms. This makes them ideal for mapping the distribution of baryons across the cosmos, even in regions that are largely invisible to traditional telescopes. Recent advancements in radio astronomy have made it possible to detect and analyze more FRBs than ever before. Telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or WHIM, have been instrumental in discovering dozens of these bursts, each providing a new piece of the puzzle. By combining data from multiple FRBs, astronomers are beginning to build a clearer picture of where baryons might be hiding, from the outskirts of galaxies to the vast voids between them. What's truly remarkable is that FRBs are not just helping us locate missing baryons, they're also shedding light on the structure of the universe itself. By tracing the paths of these bursts, scientists can map the cosmic web, the intricate network of filaments and voids that make up the large-scale structure of the universe. This dual role makes FRBs one of the most exciting and versatile tools in modern astronomy. As we continue to detect more FRBs and refine our techniques for analyzing them, their potential to solve the missing baryon problem grows. These fleeting bursts of radio waves, once a cosmic mystery, are now guiding us toward a deeper understanding of the universe's hidden matter. And with every new discovery, we move closer to unraveling one of the greatest puzzles in cosmology. Now, let's turn our attention to another fascinating clue in the search for missing baryons: the Lyman-alpha forest. This phenomenon might sound like something out of a dense scientific textbook, but it's actually a powerful tool that helps astronomers map the distribution of matter in the universe. So, what exactly is the Lyman-alpha forest, and how does it connect to the missing baryon problem? The Lyman-alpha forest refers to a series of absorption lines that appear in the spectra of distant quasars, which are incredibly bright objects powered by supermassive black holes. When light from these quasars travels through the universe, it passes through clouds of gas, primarily hydrogen, that lie between the quasar and us. These clouds absorb specific wavelengths of light, particularly in the ultraviolet part of the spectrum, creating a pattern of dark lines known as absorption lines. Because these lines are caused by hydrogen, and hydrogen is the most abundant element in the universe, they provide a unique window into the distribution of baryons. Here's how it works. As the quasar's light travels through space, it encounters hydrogen clouds at different distances. Each cloud absorbs light at a slightly different wavelength, depending on how far away it is and how fast it's moving due to the expansion of the universe. The result is a forest of absorption lines, each representing a different cloud of hydrogen along the line of sight. By analyzing these lines, astronomers can determine not only where the hydrogen is located, but also how much of it exists in different regions of the universe. What makes the Lyman-alpha forest so valuable is its ability to reveal the presence of baryons in the intergalactic medium, the vast space between galaxies. Much of the missing baryons are thought to be hiding in this diffuse gas, which is too faint to be seen directly. However, the absorption lines in the Lyman-alpha forest act like cosmic signposts, pointing to where these baryons might be located. By studying the patterns and densities of these lines, scientists can estimate the total amount of baryons in the universe and how they're distributed. One of the key advantages of the Lyman-alpha forest is its ability to probe the universe at different distances and times. Because quasars are so bright, they can be observed from billions of light years away, allowing astronomers to study the distribution of baryons across vast cosmic epochs. This makes it possible to track how the universe's structure has evolved over time, from the early days of galaxy formation to the present day. In recent years, advancements in spectroscopy and telescope technology have made it possible to analyze the Lyman-alpha forest with unprecedented precision. Instruments like the Hubble Space Telescope and ground-based observatories have provided detailed spectra of distant quasars, revealing intricate patterns in the absorption lines. These observations are helping scientists refine their models of the cosmic web, the large-scale structure of the universe, and pinpoint where the missing baryons might be hiding. The Lyman-alpha forest is more than just a collection of absorption lines, it's a roadmap to the universe's hidden matter. By decoding the patterns in this cosmic forest, astronomers are piecing together the story of where baryons reside and how they shape the universe around us. As we continue to explore this clue, we move closer to solving one of the most enduring mysteries in cosmology. And with every new discovery, the Lyman-alpha forest reveals more about the intricate tapestry of the cosmos. Now, shifting our focus to another critical piece of the puzzle, let's explore how galaxy formation simulations are shedding light on the missing baryon problem. These simulations, powered by some of the most advanced supercomputers in the world, allow scientists to recreate the universe's evolution from its earliest moments to the present day. By modeling the complex interactions of dark matter, gas, and stars, these simulations provide a virtual laboratory for understanding where baryons might be hiding and how they've changed over billions of years. At the heart of these simulations is the idea that baryons, the ordinary matter that makes up stars, planets, and even us, are deeply intertwined with the invisible scaffolding of dark matter. Dark matter, which makes up about 85% of the universe's mass, forms vast structures called halos. These halos act as gravitational wells, pulling in gas and dust, which eventually collapse to form galaxies. But here's the catch: not all the baryons end up in galaxies. A significant portion is thought to reside in the intergalactic medium, the vast spaces between galaxies where they're much harder to detect. Galaxy formation simulations help scientists track the journey of baryons over cosmic time. They start by modeling the early universe just after the Big Bang, when the first seeds of structure began to form. As the universe expanded and cooled, dark matter halos grew, and gas began to flow into them. Some of this gas collapsed to form stars and galaxies, while the rest was heated and pushed out into the intergalactic medium by processes like supernova explosions and the activity of supermassive black holes. By simulating these processes, researchers can predict how much baryonic matter should be in galaxies versus how much should be floating in the spaces between them. One of the key insights from these simulations is that baryons are not evenly distributed. Instead, they follow the intricate web-like structure of the cosmic web, the large-scale framework of the universe. Simulations show that baryons tend to accumulate in the densest regions of this web, such as galaxy clusters, but also flow along the filaments that connect them. This means that a significant portion of the missing baryons could be hiding in these filaments, where they're too diffuse to be easily observed. Another important aspect of these simulations is their ability to account for feedback mechanisms, processes that can push baryons out of galaxies and into the intergalactic medium. For example, when massive stars explode as supernova, they release enormous amounts of energy, heating the surrounding gas and driving it out of galaxies. Similarly, supermassive black holes at the centers of galaxies can produce powerful jets and winds that eject baryons into intergalactic space. By incorporating these feedback processes, simulations provide a more accurate picture of where baryons might be located and how they move over time. Recent advancements in computational power have allowed scientists to run simulations with unprecedented detail. These high-resolution models can track the behavior of baryons on smaller scales, revealing how they interact with dark matter and how they're influenced by cosmic events like galaxy collisions. This level of detail is crucial for making precise predictions about the distribution of baryons and for guiding observational efforts to find them. Galaxy formation simulations are more than just theoretical tools, they're a bridge between observation and theory. By comparing the results of these simulations with real-world data from telescopes, scientists can test their models and refine their understanding of the missing baryon problem. As simulations continue to improve, they'll play an increasingly important role in solving this cosmic mystery, helping us piece together the story of where the universe's ordinary matter has gone and how it shapes the cosmos we see today. Now, let's turn our attention to one of the most dramatic events in the universe, supernova, and how these colossal explosions play a crucial role in the missing baryon mystery. When a massive star reaches the end of its life, it doesn't fade quietly. Instead, it goes out with a bang, releasing an incredible amount of energy in a supernova explosion. This explosion doesn't just light up the cosmos, it also has a profound impact on the distribution of baryons, the ordinary matter that makes up everything we can see. During a supernova, the outer layers of the star are violently ejected into space at speeds of thousands of kilometers per second. This explosive force doesn't just scatter the star's material, it also heats and ionizes the surrounding gas, pushing it out of the galaxy and into the intergalactic medium. In this way, supernovae act like cosmic catapults, flinging baryons far beyond the confines of their home galaxies and into the vast, diffuse regions between them. This process is one of the key ways baryons can end up in places where they're much harder to detect, contributing to the missing baryon problem. But supernovae don't just eject baryons randomly. The energy they release creates shock waves that ripple through the surrounding gas, compressing it and triggering the formation of new stars and galaxies. At the same time, these shock waves can also push gas out of galaxies entirely, redistributing baryons across the cosmic web. This dual role, both seeding new structures and scattering baryons into the void, makes supernova a critical piece of the puzzle when it comes to understanding where the universe's ordinary matter has gone. One of the most fascinating aspects of supernova is their ability to enrich the intergalactic medium with heavy elements like iron and oxygen, forged in the hearts of stars. These elements, which are essential for the formation of planets and life, are carried along with the ejected baryons spreading throughout the cosmos. This means that the missing baryons aren't just ordinary hydrogen and helium, they're also laced with the building blocks of everything from rocky planets to living organisms. By studying the distribution of these elements, scientists can trace the journey of baryons ejected by supernova and gain new insights into their whereabouts. Supernova also play a key role in regulating the growth of galaxies. When a galaxy experiences a burst of star formation, it often leads to a wave of supernova. These explosions can heat the surrounding gas so much that it becomes too hot to collapse and form new stars, effectively putting the brakes on further star formation. This feedback mechanism ensures that galaxies don't grow too quickly, but it also means that a significant amount of baryonic matter is pushed out of galaxies and into the intergalactic medium, where it becomes part of the missing baryon problem. Recent observations and simulations have shown that supernovae are far more influential than we once thought. Not only do they shape the galaxies they occur in, but they also have a lasting impact on the large-scale structure of the universe. By ejecting baryons into the cosmic web, supernovae help to fill in the gaps between galaxies, creating a more connected and dynamic universe. This makes them a vital clue in the search for the missing baryons, as they provide a mechanism for how ordinary matter can be spread across vast distances and hidden in plain sight. As we continue to study supernovae and their effects, we're gaining a clearer picture of how these explosive events contribute to the missing baryon problem. From ejecting baryons into intergalactic space to enriching the cosmos with heavy elements, supernovae are a powerful force in shaping the universe we see today. And as we piece together their role in the cosmic story, we're one step closer to solving the mystery of where all the baryons have gone. Now, let's journey back in time to one of the most transformative periods in the history of the universe, the Epoch of reionization. This era, which began roughly 400 million years after the Big Bang, marks the moment when the first stars and galaxies ignited, flooding the cosmos with light and fundamentally altering its structure. But what does this ancient chapter of cosmic history have to do with the missing baryon problem? As it turns out, quite a lot. During the Epoch of reionization, the universe was a very different place. After the Big Bang, the cosmos was filled with a dense fog of neutral hydrogen gas, which absorbed light and kept the universe dark. But as the first stars and galaxies began to form, their intense ultraviolet radiation started to ionize this gas, stripping electrons from hydrogen atoms and turning the fog into a transparent sea of charged particles. This process, known as reionization, didn't just light up the universe, it also had a profound impact on the distribution of baryons. The energy released by these early stars and galaxies didn't just ionize the gas, it also heated it, causing it to expand and spread out across the cosmos. This expansion pushed baryons into the intergalactic medium, where they became part of the vast cosmic web. In this way, the Epoch of reionization played a key role in shaping the large-scale structure of the universe and determining where baryons would ultimately end up. But it also made these baryons harder to detect, as the ionized gas became more diffuse and less visible to our telescopes. One of the most intriguing aspects of this period is how it connects to the missing baryon problem. The same ultraviolet radiation that ionized the gas also helped to distribute baryons across the universe, scattering them into regions where they're difficult to observe. This means that some of the missing baryons we're searching for today may have been pushed into these hard-to-detect regions during the Epoch of reionization. By studying this era, scientists can gain new insights into how baryons were distributed in the early universe and where they might be hiding now. But the Epoch of reionization wasn't just about scattering baryons, it also played a crucial role in the formation of galaxies. As the first stars and galaxies ionized their surroundings, they created bubbles of transparent gas that allowed light to travel freely. These bubbles eventually grew and merged, filling the universe with light and paving the way for the formation of larger, more complex structures. This process not only shaped the distribution of baryons, but also set the stage for the galaxies and galaxy clusters we see today. Recent observations of distant quasars and galaxies have provided valuable clues about this pivotal period. By studying the light from these ancient objects, scientists can trace the history of reionization and learn more about how baryons were distributed during this time. These observations suggest that reionization was a patchy and uneven process, with some regions ionizing earlier than others. This patchiness may have left behind pockets of baryons in different states, some of which could still be hidden in the intergalactic medium today. The epoch of reionization also highlights the interconnected nature of cosmic processes. The same stars and galaxies that lit up the universe also played a key role in redistributing its baryons, shaping the cosmic web and influencing the evolution of galaxies. This makes reionization a critical piece of the puzzle when it comes to understanding the missing baryon problem. By unraveling the mysteries of this ancient era, we can gain new insights into where the universe's ordinary matter has gone and how it has shaped the cosmos we see today. As we continue to explore the epoch of reionization, we're not just uncovering the history of the universe, we're also shedding light on one of its greatest mysteries. From the first stars that illuminated the cosmos to the baryons they scattered across the void, this era holds the key to understanding how the universe evolved and where its missing matter might be hiding. And as we piece together this cosmic story, we're one step closer to solving the mystery of the missing baryons. Now, let's turn our attention to the outskirts of galaxies, where another piece of the missing baryon puzzle might be hiding: galaxy halos. These vast, extended regions surrounding galaxies are often overlooked, but they could hold the key to locating some of the universe's elusive ordinary matter. Galaxy halos are enormous, diffuse structures that extend far beyond the visible edges of galaxies. They're made up of a mix of dark matter, gas, and potentially missing baryons. While we can't see these halos directly, their presence is inferred through their gravitational effects on the motion of stars and gas within galaxies. But here's the catch: the baryons in these halos are incredibly difficult to detect. They're spread out over such vast distances that they don't emit enough light or radiation for our current telescopes to pick up easily. One reason baryons might end up in galaxy halos is due to the powerful forces at play during galaxy formation. As galaxies grow and evolve, they pull in gas from their surroundings through gravity. Some of this gas falls into the galaxy itself, fueling star formation, while the rest gets pushed out into the halo. Supernova, the explosive deaths of massive stars, can also eject baryons into these outer regions, scattering them far from the galaxy's core. Over time, this process can create a reservoir of baryons in the halo where they remain hidden from view. Another factor that makes these baryons hard to detect is their temperature. The gas in galaxy halos is often in a warm hot state, meaning it's too hot to emit visible light but not hot enough to produce strong X-ray signals. This puts it in a kind of observational blind spot where it's too faint for most telescopes to detect. However, recent advancements in technology are beginning to change that. Instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope are giving us new tools to probe these elusive regions, searching for faint traces of ionized gas that could reveal the presence of missing baryons. Interestingly, galaxy halos aren't just passive reservoirs, they're also dynamic environments. Gas from the halo can sometimes fall back into the galaxy, providing fuel for new generations of stars. This cyclical process, known as galactic recycling, suggests that baryons in halos aren't entirely lost, they're just temporarily out of sight. By studying these inflows and outflows, scientists can gain a better understanding of how baryons move between galaxies and their halos, and how this movement might contribute to the missing baryon problem. One of the most promising ways to detect baryons in galaxy halos is through absorption lines in the spectra of distant quasars. When light from a quasar passes through a galaxy's halo, some of it gets absorbed by the gas in the halo, creating distinct lines in the quasar's spectrum. By analyzing these lines, astronomers can determine the composition, temperature, and density of the gas, providing clues about the baryons hidden within. This technique has already revealed the presence of ionized gas in the halos of many galaxies, suggesting that a significant portion of the missing baryons could be lurking in these extended regions. The study of galaxy halos also highlights the importance of looking beyond the obvious. While much of our focus has been on the bright, dense regions of galaxies, the answers to some of cosmology's biggest questions might lie in the faint, diffuse outskirts. By exploring these hidden realms, we're not just searching for missing baryons, we're also uncovering new insights into how galaxies form, evolve, and interact with their surroundings. As we continue to investigate galaxy halos, we're reminded that the universe often hides its secrets in plain sight, or in this case, just beyond it. The missing baryons in these extended regions may be elusive, but with each new observation and technological breakthrough, we're getting closer to finding them. And as we do, we're piecing together a more complete picture of the cosmos, one halo at a time. Next, we'll explore how supermassive black holes, the most powerful objects in the universe, might be influencing the distribution of baryons and contributing to the missing baryon problem. Now, let's shift our focus to one of the most fascinating and powerful objects in the universe, supermassive black holes. These cosmic giants lurking at the centers of galaxies don't just consume matter, they also play a surprising role in shaping the distribution of baryons across the cosmos. Supermassive black holes are incredibly dense regions of space where gravity is so strong that not even light can escape, but their influence extends far beyond their event horizons. As matter spirals into a black hole, it forms a swirling disk of gas and dust, heating up to extreme temperatures. This process releases enormous amounts of energy, often in the form of powerful jets and radiation. These energetic outbursts can have a profound impact on the surrounding galaxy, including the distribution of baryons. One way supermassive black holes influence baryons is by heating the gas in their vicinity. When the black hole's jets and radiation interact with the surrounding gas, they can heat it to incredibly high temperatures. This hot gas becomes less likely to collapse and form stars, effectively halting star formation in certain regions of the galaxy. Instead, the heated gas can be pushed outward, away from the galaxy's core and into the intergalactic medium. This process, known as feedback, can redistribute baryons on a massive scale, scattering them far from their original locations. But that's not all. Supermassive black holes can also eject gas from galaxies entirely. In some cases, the energy released by a black hole is so intense that it can blow gas out of the galaxy at incredible speeds. These outflows, often referred to as galactic winds, can carry baryons into the vast regions of space between galaxies. Once there, the baryons become part of the intergalactic medium, where they're much harder to detect. This ejection process could explain why some baryons seem to be missing. They've been flung far beyond the reach of our telescopes. Interestingly, the impact of supermassive black holes isn't limited to their host galaxies. The jets and outflows they produce can extend for thousands or even millions of light years, affecting the surrounding cosmic environment. These jets can heat the gas in galaxy clusters, preventing it from cooling and forming new stars. This means that supermassive black holes don't just influence the baryons in their own galaxies, they can also shape the distribution of baryons on much larger scales. The role of supermassive black holes in the missing baryon problem highlights the interconnected nature of the universe. These enigmatic objects don't just sit quietly at the centers of galaxies. They actively shape their surroundings, redistributing matter and energy in ways we're only beginning to understand. By studying the effects of black holes on baryons, scientists can gain new insights into how galaxies evolve and how matter is distributed throughout the cosmos. As we continue to explore the mysteries of supermassive black holes, we're reminded that even the most extreme objects in the universe are part of a larger cosmic story. Their influence on baryons is just one piece of the puzzle, but it's a crucial one. By understanding how black holes shape the distribution of matter, we're getting closer to solving the missing baryon problem and uncovering the secrets of the universe itself. Next, we'll take a closer look at the intracluster medium, the hot gas that fills the spaces between galaxies in clusters, and how it might hold clues to the missing baryons. Now let's turn our attention to the vast spaces between galaxies, where another piece of the missing Baryon puzzle might be hiding: the intracluster medium. This hot, diffuse gas fills the regions between galaxies within galaxy clusters, and it's one of the most intriguing places to search for the elusive baryons. Galaxy clusters are the largest structures in the universe, containing hundreds or even thousands of galaxies bound together by gravity. But galaxies aren't the only thing these clusters hold. The space between them is filled with a thin, incredibly hot gas known as the intracluster medium. This gas is so hot, reaching temperatures of millions of degrees, that it emits X-rays, making it detectable with the right instruments. The intracluster medium is a significant reservoir of baryons. In fact, it's estimated that the gas in the intracluster medium contains more baryons than all the stars and galaxies within the cluster combined. This makes it a prime candidate for explaining where some of the missing baryons might be hiding. But why is this gas so hard to detect? The answer lies in its temperature and density. The intracluster medium is extremely hot and spread out, making it difficult to observe with traditional optical telescopes. Instead, scientists rely on X-ray telescopes like Chandra to study this faint, high-energy glow. One of the key ways the intracluster medium contributes to the missing baryon problem is through its sheer volume. The gas isn't confined to small pockets, it permeates the entire cluster, stretching across millions of light years. This means that even though the gas is thin, there's so much of it that it adds up to a significant amount of baryonic matter. When combined with the baryons in galaxies and other structures, the intracluster medium helps fill in some of the gaps in our cosmic accounting. But the story doesn't end there. The intracluster medium also plays a role in the evolution of galaxy clusters. As galaxies move through the cluster, they interact with the hot gas, stripping away some of their own gas in the process. This gas then becomes part of the intracluster medium, further enriching it with baryons. Over time, this process can redistribute baryons from individual galaxies into the wider cluster environment, making them harder to detect in their original locations. Interestingly, the intracluster medium isn't just a passive reservoir of gas, it's also shaped by the forces at work within the cluster. Supermassive black holes, as we discussed earlier, can heat the gas and drive outflows, while gravitational interactions between galaxies can stir the gas and redistribute it. These dynamic processes mean that the intracluster medium is constantly changing, adding another layer of complexity to the search for missing baryons. By studying the intracluster medium, scientists are uncovering new clues about the distribution of baryons in the universe. This hot, diffuse gas might not be as flashy as galaxies or black holes, but it's a critical piece of the cosmic puzzle. As we continue to explore its properties, we're getting closer to understanding how baryons are distributed on the largest scales, and solving the mystery of the missing baryons. Next, we'll explore how magnetic fields, often overlooked in the cosmic story, might also play a role in shaping the distribution of baryons across the universe. Now, let's shift our focus to an often overlooked player in the cosmic drama: magnetic fields. While we tend to think of gravity as the dominant force shaping the universe, magnetic fields also play a subtle yet significant role in influencing the distribution and detection of baryons. These invisible forces, generated by the motion of charged particles, weave through the cosmos, shaping the behavior of gas and plasma on both small and large scales. Magnetic fields are found everywhere in the universe, from the surfaces of stars to the vast expanses of intergalactic space. They can stretch across millions of light years, threading through galaxy clusters and the cosmic web. But how do these fields affect baryons? For one, they can influence the movement of ionized gas, which makes up a significant portion of the baryonic matter in the universe. Magnetic fields can channel this gas into specific regions, creating structures like filaments or sheets, or even preventing it from collapsing into galaxies. This means that baryons might not always be where we expect them to be, adding another layer of complexity to the missing baryon problem. One of the key challenges in studying magnetic fields is their invisibility. Unlike stars or gas clouds, magnetic fields don't emit light, making them difficult to detect directly. Instead, scientists rely on indirect methods, such as observing the polarization of light or the behavior of cosmic rays, to map these fields. For example, when light passes through a magnetized region, its polarization can change, providing clues about the strength and orientation of the magnetic field. Similarly, cosmic rays' high-energy particles traveling through space can be deflected by magnetic fields, revealing their presence and structure. Magnetic fields also play a role in heating and stirring the intergalactic medium. In galaxy clusters, for instance, the intracluster medium is not only hot but also magnetized. These fields can transfer energy to the gas, keeping it ionized and preventing it from cooling and forming stars. This process helps explain why some regions of the universe remain filled with diffuse, hot gas rather than collapsing into denser structures. By influencing the temperature and motion of baryons, magnetic fields can effectively hide them from detection, especially in regions where traditional methods struggle to penetrate. Another intriguing aspect of magnetic fields is their ability to amplify or suppress the effects of other forces. For example, in the presence of strong magnetic fields, the movement of ionized gas can be slowed or redirected, altering the way baryons are distributed. This interaction can create pockets of gas that are denser or more diffuse than expected, further complicating our efforts to account for all the baryons in the universe. Additionally, magnetic fields can affect the propagation of radio waves and other signals used to detect baryons, potentially masking their presence in certain regions. Despite these challenges, scientists are making progress in understanding the role of magnetic fields in the cosmic baryon budget. Advanced simulations now incorporate magnetic fields into models of galaxy formation and the evolution of the cosmic web, providing new insights into how these fields shape the distribution of baryons. Meanwhile, cutting-edge telescopes and instruments are being developed to better observe and measure magnetic fields across the universe, offering hope for uncovering their full impact on the missing baryon problem. As we continue to explore the interplay between magnetic fields and baryons, one thing becomes clear: these invisible forces are far from insignificant. They add a layer of complexity to the cosmic puzzle, reminding us that the universe is full of subtle, interconnected processes. By unraveling the mysteries of magnetic fields, we're not only getting closer to solving the missing baryon problem, but also deepening our understanding of the forces that shape the cosmos. Next, we'll take a closer look at how scientists are attempting to account for all the baryons in the universe through a comprehensive approach known as the baryon census. Now, let's turn our attention to a critical tool in the quest to solve the missing baryon problem, the baryon census. Imagine trying to take a head count of every single person in a bustling city. It's a daunting task, but with the right methods, it's possible. Similarly, scientists are working to account for every baryon in the universe, piecing together observations from across the electromagnetic spectrum to build a comprehensive picture of where these elusive particles might be hiding. The baryon census is essentially a cosmic inventory, a way for researchers to tally up all the baryons in the universe by combining data from different wavelengths of light. This approach is crucial because baryons can exist in various forms: hot gas, cold gas, plasma, and more, and each form emits or absorbs light differently. By using telescopes and instruments that observe everything from radio waves to X-rays, scientists can detect baryons in environments that would otherwise remain invisible. For example, X-ray telescopes like Chandra are excellent at spotting hot gas in galaxy clusters, while ultraviolet instruments like those on the Hubble Space Telescope can detect ionized gas in the intergalactic medium. Radio telescopes, on the other hand, are adept at picking up signals from cooler, diffuse gas. By stitching together these observations, researchers can create a more complete map of baryonic matter, filling in gaps that single wavelength observations might miss. One of the key challenges in conducting a baryon census is the sheer scale of the universe. Baryons are spread across vast distances, from the dense cores of galaxies to the sparse regions of the cosmic web. To tackle this, scientists use sophisticated computer models and simulations to predict where baryons should be based on our understanding of physics and cosmology. These models are then compared with observational data, helping to refine our estimates and identify regions where baryons might be hiding. Another important aspect of the baryon census is accounting for baryons in different states. Some baryons are locked up in stars and planets, while others float freely in the intergalactic medium. Some are ionized and emit light, while others are neutral and harder to detect. By combining data from multiple wavelengths, researchers can estimate how much baryonic matter exists in each of these states, bringing us closer to solving the missing baryon problem. Recent advancements in technology have made the baryon census more accurate than ever before. New telescopes and instruments, such as the upcoming James Webb Space Telescope and the Square Kilometre Array, promise to provide even more detailed observations across a wider range of wavelengths. These tools will allow scientists to peer deeper into the universe and uncover baryons in regions that were previously beyond our reach. As we continue to refine the baryon census, one thing is clear: this comprehensive approach is essential for solving the missing baryon problem. By combining observations from across the electromagnetic spectrum and leveraging the power of simulations, we're getting closer to accounting for every baryon in the universe. And with each new discovery, we're not only solving a cosmic mystery, but also deepening our understanding of the universe's structure and evolution. Next, we'll explore how dark matter, the universe's invisible scaffolding, might hold the key to understanding the distribution of baryons and solving this enduring cosmic puzzle. Now, let's shift our focus to one of the most mysterious components of the universe, dark matter, and its intriguing connection to the missing baryon problem. While dark matter itself doesn't emit, absorb, or reflect light, making it invisible to our telescopes, its gravitational influence is undeniable. It shapes the large-scale structure of the cosmos, guiding the formation of galaxies and the cosmic web. But how does this invisible force relate to baryons, the ordinary matter we're trying to account for? Dark matter and baryons are deeply intertwined in the cosmic dance of structure formation. Think of dark matter as the scaffolding of the universe, creating the gravitational wells that pull baryons into place. Without dark matter, galaxies and galaxy clusters wouldn't have formed in the way we observe them today. This means that understanding the distribution of dark matter can give us critical clues about where baryons might be hiding. One of the key ways dark matter influences baryons is through its gravitational pull. As dark matter clumps together, it creates regions of higher density, attracting baryons to these areas. Over time, these baryons cool and condense, forming stars, galaxies, and other structures. However, not all baryons end up in these dense regions. Some are pushed out into the intergalactic medium by processes like supernova explosions or cosmic winds, creating a more diffuse distribution of baryons that's harder to detect. This relationship between dark matter and baryons is particularly important when it comes to the missing baryon problem. If we can map the distribution of dark matter, we can predict where baryons should be located, even if they're not directly visible. For example, simulations of the universe's evolution show that baryons tend to follow the gravitational pull of dark matter, accumulating in the filaments of the cosmic web and the halos surrounding galaxies. By studying these regions, scientists can narrow down the search for missing baryons. Another fascinating aspect of this relationship is how dark matter affects the temperature and state of baryons. In regions where dark matter is densely packed, baryons are often heated to extreme temperatures, becoming part of the warm-hot intergalactic medium, or WHIM. This hot, diffuse gas is one of the leading candidates for where the missing baryons might reside. By understanding how dark matter influences the heating and distribution of baryons, we can better target our observations to detect this elusive material. Recent advancements in dark matter research are also shedding light on the missing baryon problem. Techniques like gravitational lensing, which uses the bending of light by massive objects to map dark matter, are providing unprecedented insights into the distribution of both dark matter and baryons. Additionally, experiments aimed at detecting dark matter particles, such as WHIMP weakly interacting massive particles, could indirectly help us understand how baryons are distributed in the universe. As we continue to explore the role of dark matter, it's becoming increasingly clear that solving the missing baryon problem requires a holistic approach. By combining our knowledge of dark matter with observations across the electromagnetic spectrum, we can piece together a more complete picture of where baryons are hiding. This not only brings us closer to solving a cosmic mystery, but also deepens our understanding of how the universe's invisible and visible components work together to shape the cosmos we see today. Next, we'll dive into how cosmic winds, driven by the explosive power of supernova and star formation, play a role in redistributing baryons across the universe. Now, let's turn our attention to the powerful forces of cosmic winds and their role in shaping the distribution of baryons across the universe. These winds, driven by the explosive energy of supernova and the intense radiation from star formation, act like cosmic gusts, sweeping baryons out of galaxies and into the vast intergalactic medium. This process not only reshapes the structure of galaxies but also plays a crucial role in the missing baryon problem. When massive stars reach the end of their lives, they explode as supernova, releasing enormous amounts of energy. This energy doesn't just vanish, it creates shockwaves that push gas and dust outward, forming what we call cosmic winds. Similarly, the intense radiation from young, hot stars can heat surrounding gas, causing it to expand and flow outward. Together, these forces generate winds that can reach speeds of hundreds or even thousands of kilometers per second, carrying baryons far beyond the boundaries of their host galaxies. As these winds travel, they deposit baryons into the intergalactic medium, the space between galaxies. This process is particularly important because it helps explain why some baryons are so difficult to detect. Instead of being concentrated in galaxies where they're easier to observe, these baryons are spread out across vast regions of space, making them much harder to pinpoint. This redistribution of baryons is a key piece of the puzzle when it comes to understanding where the missing baryons might be hiding. One of the most fascinating aspects of cosmic winds is their ability to influence the evolution of galaxies. By pushing baryons out of galaxies, these winds can slow down or even halt star formation, effectively regulating how galaxies grow over time. This feedback mechanism ensures that galaxies don't consume all their gas too quickly, allowing them to form stars at a more sustainable rate. At the same time, the baryons ejected by these winds become part of the larger cosmic ecosystem, contributing to the formation of new structures in the intergalactic medium. Scientists have observed the effects of cosmic winds in a variety of environments, from nearby galaxies to distant quasars. For example, in starburst galaxies undergoing intense periods of star formation, cosmic winds are particularly strong, ejecting large amounts of gas and dust into the surrounding space. These observations provide valuable insights into how baryons are transported and redistributed on cosmic scales. Understanding the impact of cosmic winds is essential for solving the missing baryon problem. By studying how these winds move baryons through the universe, scientists can better predict where to look for the missing material. This includes focusing on regions of the intergalactic medium that have been enriched by cosmic winds, as well as using advanced telescopes to detect the faint signatures of baryons in these diffuse environments. As we continue to explore the role of cosmic winds, it's clear that they are a vital piece of the cosmic puzzle. By connecting the explosive power of supernova and star formation to the distribution of baryons, we gain a deeper understanding of how the universe evolves and where its missing components might be hiding. Next, we'll examine how quasars, the brightest objects in the universe, play a role in revealing the presence of baryons in the intergalactic medium. Now, let's shift our focus to the dazzling beacons of the cosmos, quasars, and their extraordinary ability to illuminate the hidden baryons scattered throughout the universe. Quasars, short for quasi-stellar radio sources, are among the brightest and most energetic objects in existence. Powered by supermassive black holes at the centers of distant galaxies, these cosmic powerhouses emit immense amounts of light and radiation, making them visible across billions of light years. But beyond their brilliance, quasars play a critical role in solving the missing baryon problem by acting as cosmic flashlights, revealing the presence of baryons in the intergalactic medium. At the heart of every quasar lies a supermassive black hole, surrounded by a swirling disk of gas and dust. As material falls into the black hole, it heats up to extreme temperatures, releasing vast amounts of energy in the form of light, X-rays, and ultraviolet radiation. This intense radiation doesn't just make quasars visible, it also ionizes the surrounding gas, stripping electrons from atoms and creating a plasma of charged particles. This ionized gas, often referred to as the intergalactic medium, is where many of the missing baryons are thought to reside. Quasars are particularly useful for studying the intergalactic medium because their light travels through vast stretches of space before reaching us. Along the way, this light interacts with the gas in the intergalactic medium, leaving behind distinct absorption lines in the quasar's spectrum. These lines, known as the Lyman-alpha forest, act like fingerprints, revealing the density, temperature, and distribution of baryons in the regions the light has passed through. By analyzing these absorption features, scientists can map out the presence of baryons in the otherwise invisible intergalactic medium. One of the most remarkable aspects of quasars is their ability to ionize gas over enormous distances. The radiation from a single quasar can travel billions of light years, ionizing gas far beyond its host galaxy. This process not only helps us detect baryons, but also provides insights into the conditions of the early universe. For example, quasars played a key role during the Epoch of reionization, a period when the first stars and galaxies formed and ionized the surrounding hydrogen gas. By studying quasars, scientists can piece together how the universe transitioned from a dark, neutral state to the ionized cosmos we see today. Observations of quasars have already yielded significant clues about the missing baryons. For instance, studies using the Hubble Space Telescope and other instruments have detected vast reservoirs of ionized gas in the intergalactic medium, accounting for a substantial fraction of the universe's baryons. These findings suggest that much of the missing material is not truly missing, it's just spread out in diffuse, hard-to-detect regions of space. As we continue to explore the role of quasars, it's clear that these luminous objects are invaluable tools for uncovering the secrets of the universe. By using their light to probe the intergalactic medium, scientists are piecing together the cosmic puzzle of where baryons are hiding. Next, we'll turn our attention to dwarf galaxies and their potential role in harboring some of the universe's missing baryons. Now, let's venture into the realm of dwarf galaxies, the unsung heroes of the cosmic landscape. These small, faint galaxies may not grab headlines like their larger counterparts, but they hold a treasure trove of secrets, especially when it comes to the missing baryon problem. Dwarf galaxies, with their low mass and dim glow, are often overlooked, yet they could be hiding a significant portion of the universe's elusive baryons. Dwarf galaxies are much smaller than typical galaxies like the Milky Way, often containing only a few billion stars compared to the hundreds of billions found in larger galaxies. Their faintness makes them challenging to observe, but this very characteristic might make them ideal hiding spots for missing baryons. Unlike massive galaxies, which have strong gravitational fields that can eject baryons into intergalactic space, dwarf galaxies have weaker gravity, potentially allowing them to retain more of their original baryonic material. One intriguing possibility is that dwarf galaxies could be surrounded by extended halos of gas, rich in baryons, that are difficult to detect with current technology. These halos might consist of warm or cool gas that doesn't emit much light, making it nearly invisible to traditional telescopes. However, recent advancements in observational techniques, such as radio and ultraviolet observations, are beginning to shed light on these elusive structures. For example, studies using the Green Bank telescope have detected faint signals of hydrogen gas around dwarf galaxies, hinting at the presence of these hidden baryon reservoirs. Another factor that makes dwarf galaxies fascinating is their role in the early universe. Many dwarf galaxies are thought to be relics from the cosmic dawn, forming shortly after the Big Bang. Because they have evolved relatively undisturbed over billions of years, they might preserve clues about the distribution of baryons in the universe's infancy. By studying these ancient galaxies, scientists can gain insights into how baryons were distributed and how they evolved over cosmic time. Despite their potential, dwarf galaxies present unique challenges for astronomers. Their low luminosity makes them hard to detect, and their small size means they don't produce as much observable radiation as larger galaxies. Additionally, the gas in and around dwarf galaxies is often too cool to emit X-rays, which are typically used to detect hot gas in the universe. This means that uncovering the baryons in dwarf galaxies requires innovative approaches, such as combining data from multiple wavelengths or using indirect methods like gravitational lensing. As we continue to explore these tiny cosmic islands, it's becoming clear that dwarf galaxies could play a crucial role in solving the missing baryon problem. Their faintness and low mass might make them elusive, but they could be holding the key to understanding where the universe's baryons have gone. Next, we'll turn our attention to the role of cosmic inflation and how it might have influenced the distribution of baryons in the early universe. Now let's take a step back in time, way back to the very beginning of the universe. Here, we encounter one of the most fascinating theories in cosmology, cosmic inflation. This rapid expansion of space, occurring just a fraction of a second after the Big Bang, might hold critical clues about the distribution of baryons in the universe today. Cosmic inflation proposes that the universe underwent an exponential expansion, growing from a tiny speck to an enormous size in an incredibly short time. This sudden stretching of space had profound effects on the distribution of matter, including baryons. As the universe expanded, tiny quantum fluctuations were magnified, creating the seeds for the large-scale structures we see today, like galaxies and galaxy clusters. But how does this connect to the missing baryon problem? During inflation, baryons along with other particles were spread out across the rapidly expanding universe. The distribution of these baryons was influenced by the same quantum fluctuations that shaped the cosmic web. As inflation ended and the universe continued to evolve, these fluctuations became the framework for where baryons would eventually gather. Some regions became denser, forming galaxies and clusters, while others remained sparse, leaving baryons scattered in the vast intergalactic medium. One intriguing idea is that inflation might have caused baryons to become diluted across the universe. As space stretched, baryons could have been spread so thinly that they became difficult to detect, especially in regions far from galaxies. This could explain why a significant portion of baryons remains unaccounted for. They might be hiding in these diffuse, hard-to-observe areas. Another possibility is that inflation set the stage for the formation of the cosmic web. the vast network of filaments and voids that we discussed earlier. These filaments, rich in dark matter and gas, could have trapped baryons, making them harder to detect with current technology. In this way, cosmic inflation not only shaped the universe's structure, but also influenced where baryons ended up. While inflation provides a compelling explanation for the initial distribution of baryons, it also raises new questions. For instance, how did the baryons interact with dark matter during this rapid expansion? And how did the transition from inflation to the slower expansion we see today affect their distribution? These are questions that scientists are still working to answer, using both theoretical models and observational data. As we piece together the story of cosmic inflation, it's clear that this early chapter of the universe's history plays a crucial role in the missing baryon mystery. By understanding how inflation shaped the distribution of matter, we can gain deeper insights into where baryons might be hiding today. Next, we'll explore another piece of the puzzle, the role of neutrinos, those nearly massless particles that might have played a part in the baryon saga. Now, shifting our focus to another intriguing piece of the puzzle, let's dive into the role of neutrinos, those elusive, nearly massless particles that might hold clues to the missing baryon problem. Neutrinos are among the most abundant particles in the universe, yet they're famously difficult to detect because they interact so weakly with matter. But their subtle influence could be key to understanding where baryons have gone. Neutrinos are produced in vast quantities during high-energy events, like nuclear reactions in stars or the explosive deaths of massive stars known as supernova. As they travel through space, they barely interact with other particles, slipping through matter almost as if it weren't there. This ghostly behavior makes them fascinating, but it also raises questions about how they might affect the distribution of baryons. One possibility is that neutrinos could have influenced the early universe's structure. During the first few moments after the Big Bang, neutrinos were moving at nearly the speed of light, carrying energy and momentum. As they zipped through the cosmos, they might have nudged baryons, subtly altering their distribution. Over billions of years, these tiny interactions could have added up, causing baryons to spread out in ways that make them harder to detect today. Another intriguing idea is that neutrinos could have played a role in heating the intergalactic medium, the diffuse gas that fills the space between galaxies. As neutrinos interacted with this gas, even weakly, they might have transferred energy, causing the gas to expand and become more diffuse. This could explain why some baryons are so thinly spread out, making them nearly invisible to our telescopes. But here's where it gets even more interesting. Neutrinos themselves are incredibly light, but they're not entirely massless. Recent experiments have shown that they have a tiny amount of mass, which means they could have contributed to the gravitational pull that shaped the universe's large-scale structure. If neutrinos helped shape the cosmic web, they might have also influenced where baryons ended up, potentially hiding them in regions we're only just beginning to explore. Of course, studying neutrinos is no easy task. Their weak interactions make them incredibly challenging to detect, and much of what we know about them comes from indirect observations. Yet, as technology advances, scientists are finding new ways to study these ghostly particles, hoping to uncover their role in the missing baryon mystery. As we continue to explore the universe's hidden corners, neutrinos remind us that even the smallest, most elusive particles can have a profound impact on the cosmos. Next, we'll turn our attention to another powerful tool in the search for missing baryons: gravitational lensing, a phenomenon that bends light and reveals the unseen. Now, let's turn our attention to a fascinating phenomenon that acts as a cosmic magnifying glass: gravitational lensing. This incredible effect occurs when massive objects, like galaxies or galaxy clusters, bend the light from objects behind them. Imagine placing a heavy ball on a stretched-out sheet. It creates a dip that warps the surface, Similarly, massive objects in space warp the fabric of spacetime, bending the path of light as it travels through the universe. This bending can magnify, distort, or even multiply the images of distant objects, giving astronomers a powerful tool to peer into regions of the cosmos that would otherwise remain hidden. So, how does gravitational lensing help us find missing baryons? When light from a distant quasar or galaxy passes through a massive object, the lensing effect can reveal the presence of matter, including baryons along its path. Even if the baryons are too faint or diffuse to detect directly, their gravitational influence can subtly alter the way light bends, leaving behind telltale clues. By carefully analyzing these distortions, scientists can map out the distribution of matter, including baryons, in the lensing region. One of the most exciting applications of gravitational lensing is its ability to uncover baryons in the warm-hot intergalactic medium, or WHIM. This elusive gas, which we've discussed earlier, is notoriously difficult to detect because it's so spread out and faint. But when light from a distant source passes through a region filled with WHIM, the lensing effect can amplify the signal, making it easier for astronomers to spot. This allows researchers to piece together where baryons might be hiding in the vast expanses between galaxies. Gravitational lensing also helps us study the large-scale structure of the universe. By observing how light bends around massive galaxy clusters, scientists can create detailed maps of the cosmic web, the intricate network of filaments and voids that make up the universe's backbone. These maps not only reveal the distribution of dark matter, but also provide insights into where baryons might be concentrated, offering a clearer picture of how matter is organized on the grandest scales. But gravitational lensing isn't just about finding baryons, it's also a window into the early universe. By studying lensed images of extremely distant galaxies, astronomers can learn about the conditions of the cosmos billions of years ago. This helps us understand how baryons have evolved over time and how they've been distributed across the universe's history. As we continue to refine our techniques and build more advanced telescopes, gravitational lensing promises to play an even bigger role in solving the missing baryon problem. It's a reminder that sometimes the universe itself provides the tools we need to uncover its deepest secrets. Next, we'll explore another high-energy phenomenon that might hold clues to the missing baryons: cosmic rays, the mysterious particles that streak through space at incredible speeds. Now, let's shift our focus to another intriguing piece of the cosmic puzzle: cosmic rays. These high-energy particles racing through space at nearly the speed of light might hold unexpected clues to the mystery of the missing baryons. But what exactly are cosmic rays and how do they connect to the baryon problem? Let's break it down. Cosmic rays are not rays in the traditional sense. They're actually particles, mostly protons and atomic nuclei, that originate from powerful cosmic events like supernova, black holes, and even distant galaxies. When these particles collide with other matter in space, they can produce secondary particles and radiation, creating a cascade of interactions that ripple through the cosmos. This process doesn't just generate energy, it can also influence the distribution and behavior of baryons in the universe. One way cosmic rays might impact baryons is through their ability to heat and ionize gas in the intergalactic medium. As these high-energy particles travel through space, they can transfer energy to the surrounding gas, raising its temperature and causing it to become ionized. This ionization process can make baryons more detectable, as ionized gas emits radiation that telescopes can pick up. In regions where baryons are otherwise too faint or diffuse to observe, cosmic rays could essentially light them up, making them easier to spot. But cosmic rays don't just help us detect baryons, they might also play a role in redistributing them. When cosmic rays interact with gas in galaxies or the intergalactic medium, they can create pressure waves that push baryons around, altering their distribution over time. This means that cosmic rays could be subtly shaping where baryons end up, whether they're concentrated in galaxies, spread out in the cosmic web, or hidden in the warm, hot intergalactic medium. Another fascinating aspect of cosmic rays is their potential to reveal the presence of baryons through indirect methods. For example, when cosmic rays collide with baryons, they can produce gamma rays or other forms of radiation that astronomers can detect. By studying these secondary emissions, scientists can infer the presence and density of baryons in regions that are otherwise invisible to our telescopes. It's like using cosmic rays as a flashlight to illuminate the dark corners of the universe where baryons might be hiding. Of course, studying cosmic rays and their connection to baryons is no easy task. These particles are incredibly energetic and difficult to track, often requiring specialized detectors on Earth or in space. But as our technology improves, so does our ability to unravel their secrets. Missions like the Alpha Magnetic Spectrometer on the International Space Station are already providing valuable data on cosmic rays, helping scientists piece together their role in the cosmic story. As we continue to explore the universe, cosmic rays remind us that even the smallest particles can have a big impact. From heating gas to redistributing matter, these high-energy travelers are more than just cosmic curiosities, they're potential keys to solving the missing baryon problem. Next, we'll turn our attention to another mysterious force shaping the universe, dark energy, and how it might be influencing the distribution of baryons over cosmic time. Now let's venture into one of the most profound mysteries of the cosmos, dark energy. This enigmatic force, which makes up about 68% of the universe, is responsible for the accelerated expansion of space itself. But how does this invisible, pervasive energy influence the distribution of baryons, the building blocks of matter we've been searching for? The connection might be more significant than we realize. Dark energy's primary role is to push galaxies apart, stretching the fabric of space over time. As the universe expands, the distances between galaxies grow, and the cosmic web, the vast network of filaments where baryons are thought to reside, stretches along with it. This expansion doesn't just affect the large-scale structure of the universe, it also impacts how baryons are distributed within it. As space stretches, the density of baryons in certain regions decreases, making them even harder to detect. In essence, dark energy could be spreading baryons thinner across the cosmos, hiding them in plain sight. But dark energy's influence doesn't stop there. It also affects the way galaxies and galaxy clusters evolve. As the universe expands, the gravitational pull between galaxies weakens, slowing down the process of galaxy formation and the accumulation of baryons within them. This means that over cosmic time, dark energy could be subtly altering where baryons end up, whether they're concentrated in galaxies, dispersed in the intergalactic medium, or tucked away in the warm, hot intergalactic medium. Another intriguing possibility is that dark energy might be interacting with baryons in ways we don't yet fully understand. While dark energy is often thought of as a smooth, uniform force, some theories suggest it could have small variations or fluctuations. These fluctuations could create pockets of higher or lower energy density, influencing the movement and distribution of baryons. If true, this would add another layer of complexity to the missing baryon problem, as we'd need to account for these subtle interactions in our models. One of the biggest challenges in studying dark energy's impact on baryons is that both are incredibly difficult to observe directly. Dark energy, by its very nature, doesn't emit light or interact with matter in ways we can easily detect. Similarly, baryons in the intergalactic medium are often too diffuse or faint to observe with current technology. However, astronomers are using indirect methods to piece together the puzzle. For example, by measuring the large-scale structure of the universe and how it evolves over time, scientists can infer the influence of dark energy on baryon distribution. As we continue to explore the universe, dark energy remains one of the most tantalizing and elusive pieces of the cosmic puzzle. its role in shaping the distribution of baryons over billions of years is a reminder of how interconnected the forces of the universe truly are. Next, we'll turn our attention to the final clue in our journey, the future of baryon detection and the groundbreaking technologies that could revolutionize our understanding of the missing baryon problem. As we near the end of our cosmic journey, let's turn our gaze toward the future, a future brimming with promise and cutting-edge technology that could finally unravel the mystery of the missing baryons. The next generation of telescopes and instruments is poised to revolutionize our understanding of the universe, offering unprecedented insights into where these elusive particles might be hiding. At the forefront of this technological leap is the James Webb Space Telescope, often hailed as the successor to Hubble. With its advanced infrared capabilities, Webb is designed to peer deeper into the cosmos than ever before, capturing light from the earliest galaxies and the faintest traces of gas in the intergalactic medium. This telescope could be the key to detecting baryons in regions that have remained invisible to us, such as the warm-hot intergalactic medium or the outskirts of galaxy clusters. By studying the light from distant quasars and galaxies, Webb may reveal the subtle signatures of baryons that have eluded detection for decades. But the James Webb Space Telescope is just the beginning. On the ground, the Square Kilometre Array, or SCAR, is set to become the largest radio telescope ever built. Spanning thousands of antennas across 2 continents, the SKA will map the universe in exquisite detail, using radio waves to trace the distribution of gas and baryons across vast cosmic distances. One of its most exciting applications will be the study of fast radio bursts, those mysterious flashes of radio energy that can act as cosmic probes. By analyzing how these bursts interact with the intergalactic medium, the SKA could provide a precise measurement of the baryon density in the universe, filling in critical gaps in our understanding. Another groundbreaking project on the horizon is the European Space Agency's Athena mission, an X-ray observatory designed to study the hot gas in galaxy clusters and the warm-hot intergalactic medium. Athena's high-resolution instruments will allow scientists to map the distribution of baryons in these regions with unparalleled accuracy, shedding light on how they've been influenced by dark energy and cosmic expansion over billions of years. These advancements aren't just about building bigger and better telescopes, they're about refining our techniques and combining data from multiple wavelengths. By integrating observations from X-ray, ultraviolet, infrared, and radio telescopes, scientists can create a more comprehensive picture of the universe's baryon content. This multi-wavelength approach will help us piece together the puzzle of where baryons are hiding and how they've been distributed over cosmic time. The future of baryon detection is not just about technology, it's about collaboration. Astronomers, physicists, and engineers from around the world are working together to design and operate these next-generation instruments. Their collective efforts are bringing us closer than ever to solving one of the universe's greatest mysteries. As we look ahead, it's clear that the tools we're building today will shape the discoveries of tomorrow. With each new telescope and every innovative technique, we're inching closer to uncovering the full story of the missing baryons, and in doing so, gaining a deeper understanding of the universe itself. The journey is far from over, but the future is bright and the answers are within reach. Now, let's take a closer look at how 2 of the most intriguing clues, the cosmic web and the warm-hot intergalactic medium, or WHIM, might intersect to shed light on the missing baryon problem. These 2 concepts, while distinct, are deeply interconnected in the grand tapestry of the universe, and together they could hold the key to solving this cosmic mystery. The cosmic web, as we've discussed, is a vast network of filaments made up of dark matter and gas, stretching across the universe like a spider's web. These filaments connect galaxies and galaxy clusters, forming the backbone of the large-scale structure of the cosmos. But what's truly fascinating is that these filaments are not empty, they're filled with gas, much of which is in the form of the WHIM. This diffuse, hot gas is incredibly difficult to detect because it doesn't emit much light, but it's thought to contain a significant portion of the universe's missing baryons. So, how do these two clues work together? Imagine the cosmic web as a highway system, with galaxies and clusters as the cities. The WHIM is like the invisible traffic flowing along these highways, gas that's too hot and spread out to be easily seen, but crucial for understanding the movement and distribution of matter in the universe. By studying the cosmic web, scientists can predict where the WHIM might be concentrated, and by observing the WHIM, they can confirm the presence of baryons in these elusive regions. One of the most promising ways to detect the WHIM within the cosmic web is through its interaction with light from distant quasars. As this light travels through the filaments of the web, it passes through the WHIM, which absorbs certain wavelengths. This creates a unique fingerprint in the quasar's spectrum, known as the Lyman-alpha forest. By analyzing these absorption lines, astronomers can map the distribution of the WHIM and, by extension, the missing baryons. But the connection doesn't stop there. Simulations of the cosmic web suggest that the WHIM isn't uniformly distributed, it's clumped in certain areas, particularly where filaments intersect. These intersections are like cosmic crossroads, where gas from different parts of the web converges, creating denser regions of the WHIM. By focusing on these hotspots, scientists can increase their chances of detecting the missing baryons. Combining observations from X-ray telescopes, ultraviolet spectrographs, and radio arrays, researchers are piecing together a more complete picture of how the cosmic web and the WHIM interact. Each wavelength of light reveals a different aspect of this relationship, from the hot gas detected in X-rays to the ionized gas seen in ultraviolet light. Together, these observations are helping us understand not just where the baryons are hiding, but how they've been shaped by the forces of the universe over billions of years. The cosmic web and the WHIM are more than just clues, they're pieces of a larger puzzle. By studying their connection, we're not only solving the mystery of the missing baryons, but also gaining deeper insights into the structure and evolution of the universe itself. As we continue to explore these cosmic highways and the invisible traffic flowing through them, we're one step closer to uncovering the full story of the universe's hidden matter. Now, let's turn our attention to another fascinating intersection in the search for missing baryons, the combination of fast radio bursts and the Lyman-alpha forest. These two phenomena, though seemingly unrelated, offer complementary insights that could help us piece together the cosmic puzzle of where the universe's missing matter resides. Fast radio bursts, or FRB, are incredibly brief but intense flashes of radio waves that originate from distant galaxies. While their exact origins remain a mystery, their fleeting nature makes them powerful tools for probing the universe. As these bursts travel across vast distances, they pass through various regions of space, including the cosmic web and the warm, hot intergalactic medium. Along the way, they interact with the gas in these regions, leaving behind subtle clues about the density and distribution of baryons. On the other hand, the Lyman-alpha forest, as we've discussed, is a series of absorption lines in the spectra of distant quasars. These lines are created when light from the quasars passes through clouds of hydrogen gas in the cosmic web, with each line corresponding to a different density and temperature of the gas. By analyzing these lines, astronomers can map the distribution of baryons in the intergalactic medium. So, how do these two clues work together? Imagine FRBs as cosmic flashlights, illuminating the path they travel through the universe. As their radio waves pass through the cosmic web, they interact with the same gas that creates the Lyman-alpha forest. By combining the data from FRBs and the Lyman-alpha forest, scientists can cross-check their observations, creating a more detailed and accurate map of where baryons are hiding. For example, FRBs can provide precise measurements of the total amount of matter they encounter along their journey, including both ionized and neutral gas. This complements the Lyman-alpha forest, which primarily traces neutral hydrogen. Together, these observations allow researchers to account for a broader range of baryonic matter, filling in gaps that might be missed by using just one method. Moreover, FRBs can help us study regions of the cosmic web that are too faint or diffuse to be detected through the Lyman-alpha forest alone. Because FRBs are so bright, they can reveal the presence of gas in areas that might otherwise go unnoticed. This dual approach not only enhances our understanding of the missing baryons, but also provides a more comprehensive picture of the large-scale structure of the universe. As technology advances, the potential for combining these two methods grows even greater. New radio telescopes like the Square Kilometre Array promise to detect more FRBs with unprecedented precision, while next-generation space telescopes will improve our ability to study the Lyman-alpha forest. Together, these tools will allow us to probe deeper into the cosmic web, uncovering the hidden baryons that have eluded us for so long. By merging the insights from fast radio bursts and the Lyman-alpha forest, we're not just solving the mystery of the missing baryons, we're also gaining a richer understanding of how the universe is structured and how it has evolved over time. This collaborative approach highlights the power of combining different observational techniques, bringing us closer to unraveling one of the most enduring puzzles in cosmology. Now, let's shift our focus to another dynamic duo in the cosmic quest for missing baryons, supernova and cosmic winds. These powerful forces play a crucial role in shaping the distribution of matter in the universe, and their interplay could hold the key to understanding where the missing baryons have gone. Supernova, the explosive deaths of massive stars, are among the most energetic events in the cosmos. When a star reaches the end of its life and explodes, it releases an enormous amount of energy and ejects its outer layers into space. This material, rich in baryons, is flung far and wide, scattering across the surrounding regions. These ejected baryons can travel vast distances, eventually becoming part of the intergalactic medium or settling into the halos of nearby galaxies. But supernova don't act alone. They are often accompanied by cosmic winds, which are streams of charged particles propelled by the intense energy of star formation and supernova explosions. These winds can carry baryons even further, pushing them out of galaxies and into the vast expanses of intergalactic space. Over time, this process can redistribute baryons on a cosmic scale, spreading them across the universe in ways that make them difficult to detect. The interaction between supernova and cosmic winds creates a feedback loop that influences the evolution of galaxies and the distribution of baryons. For instance, in regions with intense star formation, multiple supernova can occur in quick succession, generating powerful winds that sweep through the galaxy. These winds can clear out baryons from the central regions, depositing them in the outer reaches of the galaxy or even beyond its boundaries. This redistribution not only affects the galaxy itself, but also contributes to the enrichment of the intergalactic medium with baryonic matter. Interestingly, this process isn't uniform across the universe. In some galaxies, supernova and cosmic winds are so strong that they can expel baryons entirely, sending them into the cosmic web. In others, the winds may be weaker, allowing baryons to remain closer to their host galaxies. This variability adds another layer of complexity to the missing baryon problem, as it means baryons can be found in a wide range of environments, from the dense cores of galaxies to the diffuse filaments of the cosmic web. To better understand this interplay, scientists rely on sophisticated computer simulations that model the effects of supernova and cosmic winds over billions of years. These simulations help researchers predict where baryons might end up and how their distribution changes over time. By comparing these predictions with observations, astronomers can refine their models and gain deeper insights into the role of these processes in the missing baryon problem. As we continue to study supernova and cosmic winds, We're not just uncovering the fate of missing baryons, we're also learning more about the life cycles of galaxies and the forces that shape the universe. This exploration highlights the intricate connections between different cosmic phenomena and reminds us that solving the missing baryon problem requires a holistic approach, one that considers the many ways in which matter is moved and transformed across the cosmos. As we bring our exploration of the missing baryon problem to a close, let's take a moment to reflect on the 25 clues we've uncovered. Each one offers a unique piece of the puzzle, shedding light on where these elusive baryons might be hiding and how they shape the universe we observe today. From the intricate filaments of the cosmic web to the faint whispers of the warm, hot intergalactic medium, and from the explosive power of supernova to the subtle influence of dark energy, every clue brings us closer to solving this cosmic mystery. The cosmic web, with its vast network of dark matter and gas, provides a framework for understanding how baryons could be distributed across the universe. The warm, hot intergalactic medium, though difficult to detect, hints at a reservoir of baryons in the spaces between galaxies. X-ray observations and ultraviolet spectroscopy have allowed us to peer into these hidden realms, revealing the faint signatures of ionized gas. Meanwhile, phenomena like the Sunyaev-Zeldovich effect and fast radio bursts serve as cosmic probes, helping us measure the density and distribution of baryons in ways we never thought possible. Simulations of galaxy formation and the role of supernova and cosmic winds have shown us how baryons can be ejected and redistributed across vast distances. The epoch of reionization and the influence of black holes remind us that the early universe played a crucial role in shaping the baryonic landscape we see today. And as we look to the future, technologies like the James Webb Space Telescope and the Square Kilometre Array promise to revolutionize our ability to detect and study these missing baryons. But the search for missing baryons is more than just a scientific endeavor. It's a journey that connects us to the fundamental nature of the universe. Every clue we uncover not only brings us closer to solving this mystery, but also deepens our understanding of how galaxies form, how matter evolves, and how the cosmos itself came to be. The missing baryon problem is a reminder that the universe is full of surprises, and that there is still so much we have yet to discover. As we continue to explore the cosmos, one thing is certain: the quest to understand the universe's mysteries is far from over. With each new discovery, we take another step toward unraveling the secrets of the cosmos, and in doing so, we gain a deeper appreciation for the beauty and complexity of the universe we call home. So as we close this chapter, let's stay curious, stay inspired, and keep looking to the stars, because the next great discovery could be just around the corner. If you enjoyed this journey through the cosmos, don't forget to like, subscribe, and hit the notification bell to stay updated on our latest explorations. Until next time, keep wondering, keep exploring, and keep reaching for the